If the sun is truly as hot as we're told, then why is it that the higher we climb, the colder we feel? Above the clouds, among peaks draped in eternal ice, we are technically closer to the blazing star of our system. And yet the ice remains untouched, frozen. How can this be? We've been taught that the sun's surface burns at millions of degrees and that its energy warms the earth with precision and consistency. But perhaps the real question has never been just how hot is the sun, but rather, how does heat behave in different environments? For heat, after all, isn't merely a matter of proximity, but of air density, atmospheric pressure, of absorption and energy retention. High up in the mountains, the air is thin, light and rarefied. There are fewer molecules to hold the heat. Solar radiation does arrive, but finds little to warm. Down here at sea level, the air is dense, compact, vibrant, full of matter to absorb and conserve the sun's energy. And that's why we feel warmer, even though we're farther from the sun. The sun doesn't heat like a bonfire by direct contact. It sends waves, invisible frequencies that interact with whatever lies in their path. So while the sun may be closer to these mountain peaks, its energy is less effective at higher altitudes where the atmosphere is thinner, and so the frigid air can support ice even as it faces the sun. Closer to the equator, where the sun's rays hit the earth more directly, we experience summer's warmth. Here, the intensity of sunlight is greater. As I mentioned earlier, the air is denser, which means more particles to absorb the energy of the sun and thus retain the heat. Yet if we were to eliminate all variables, if we could somehow isolate a single molecule of sunlight, would we find it scorching hot or mildly tepid? The truth is, it's the dance between light and air, between radiation and matter that defines the warmth we feel. It's not just about how hot the sun is, but how that heat interacts with our world. As I said before, the sun doesn't heat like a bonfire. It bathes the earth in a spectrum of radiation, a radiant energy that warms our world, drives our weather, and sustains life as we know it. But this energy, it doesn't just magically stop at the upper atmosphere. It penetrates into the heart of our planet, albeit in a gradually diminishing intensity as it descends. Even deep within the Earth's core, where rocks are transformed into a sea of molten metal, the sun's rays reach down, penetrating the darkness, albeit in a weakened state. Here, 4,500 miles beneath our feet, the sun's energy touches the very core of the Earth. The sun's rays, they travel through space for 94 million miles. They pass through layers of atmosphere, each slightly cooler than the last, and still they carry the imprint of their stellar birthplace. Deep inside the Earth, the sun's energy, it's not as hot as it left the sun, but it's still there. So how hot is the sun? Perhaps the question itself is a mirage, an illusion born from our perspective. For the sun, it doesn't just radiate heat, it radiates light, a visual spectacle that coincides with, but isn't synonymous with, thermal energy. Seeing the sun's light, we infer its heat, extrapolate its temperature. But what if the true nature of solar heat is more nuanced, more intricate, tied to how its energy is received, absorbed, and retained by our world? What if the sun's heat isn't a fixed quantity, but a dynamic interaction, a dialogue between radiation and matter? In a universe where nothing is as simple as it seems, the temperature of the sun remains a luminous enigma, a puzzle where the pieces don't fit neatly into our deterministic models. Thank you for watching.